So now we understand that the universe is expanding, uh, that the distance between the galaxies is increasing with time, just like you see uh, the resins in a bread. Even you put some Easter in the loaf and resin and put it in the oven, and the bread in the oven expands overall, and the distance between the resin uh, uh, also expand with it. But the galaxies are not expanding, just like the resin inside the bread does not expand. Why? The answer to this is that they are bound together by the gravity of unknown dark entity. So if the universe is expanding but the galaxies are not expanding, why? Because there is some unknown dark entity which is keeping them together. This dark entity, not now known to us, is as a dark matter. To understand the presence of the dark matter, let us move uh, further apart. That this is a very famous cluster of galaxies known as the COMA cluster of galaxies. This is distributed within few millions light years with a mass about 1 quadrillion of the mass of the sun times the mass of the sun, and contains hundreds and tens and hundreds of galaxies inside this. So this is also famous historically because this is studied by this scientist named Zwicky, who is responsible for the discovery of the dark matter. He studied the motions of the galaxies within the COMA cluster and found that they are moving too fast, about 1000 km per second, to remain confined by COMA's gravitational field. But he asked, so why COMA cluster is still there? Why not all the galaxies are streamed away from each other if they are moving so fast relative to each other? They must have flown away by now. So what Zwicky postulated that the COMA cluster, in addition to the galaxies we could see, is filled with the dark matter. And the gravity, try to imagine this, that the COMA cluster, in the COMA cluster there are galaxies, but the COMA cluster is filled with the dark matter. And the gravity of that dark matter, to which we cannot see, must be keeping the galaxies within the COMA cluster. So within the COMA cluster, the galaxies were moving fast enough, so they must have now flown away by now, but they were not. So the dark matter, the presence of the dark matter, which is filled in the COMA cluster, is responsible, which we cannot see, keeping the galaxies within the COMA cluster from flying off into extra cluster space. He really is the first one, Zwicky is the first one to predict and study the concept of dark matter in detail, and concluded that the cluster of galaxies are mostly made up of dark matters. So looking at the COMA cluster, if you look at the COMA cluster, you can imagine that it is like the galaxies are sprinkled on the ice cream cone of the dark matter. And we know that the dark matter is there because it exerts the gravitational pull on the galaxies that we see. Now we skip forward and remind you a little bit about the motion, uh, the notion of space-time from the Einstein theory of relativity, which is a general theory of relativity. He introduces the concept that the gravity is not just a force which is acting between two massive bodies. Instead, any massive body or any type of energy actually curves the space-time in its vicinity, and other bodies or energy moves in that curved space-time, and that is how the gravity is communicated. So a massive star attracts nearby objects by distorting the space-time, and that particular star is moving around that particular massive mass of the universe. So, and using this concept, then let Einstein predict that the first, which is actually the first verification of his theory, that really the space-time gets bent in the presence of the mass, that light ray would bend in the gravitational field due to the curvature of the space-time. What that means that when we look some galaxy, so if look some galaxy which is behind some foreground of this is the bend in the curvature because of the presence of some mass, and we are trying to look this galaxy. So when we are trying to look this galaxy behind some foreground of this concentrated mass, say cluster of galaxies, then the shape of the galaxy gets distorted. So we are here, I'm seeing from the Earth trying to see this galaxy. So the shape of this galaxy will see to us as a distorted, because the light rays coming from this galaxy bend while passing through this curved space-time around the cluster of galaxies, and this is known as the gravitational lensing, we all know. So this is having been observed in the observation from the Hubble telescope and from some ground-based observatory. So you can see that this is what we are seeing here is the cluster of galaxies. These are the cluster of galaxies. Those are bright one. These bright ones are the galaxies here, and but beside that we see some very elongated structure. These are kind of these elongated structure like you see here, and those are image of the distant galaxies behind these clusters of galaxies, because the light have been passing through these clusters and have been elongated. So we can use these images to actually see the mass distribution uh, uh, of the cluster of galaxies. So if we see the mass distribution of this cluster of galaxies, if we distribute it like this, so these in this we can see these sharp peaks. These sharp peaks are the distribution of the basically the location of the galaxies, different galaxies, and these mountains of matter we see are the halo of the dark matter. So imagine that the dark matter is there all over. These galaxies are distributed within this dark matter. So this is a direct confirmation of what Zwicky has found way back in 1930. So moving further, the astronomer Vera Rubin, studying the rotation of stars around the galaxies, found something important. She studied the rotation of M33 galaxy, and what's shown here is the plot of rotational speed, or we can say the rotational velocity. This is rotational velocity as a function of the distance of the stars from the center of the galaxy M33. What we expect is that as we move out from the center towards the spiral arms, the star should be orbiting. Why it's not playing? Let's see. So when we move from the center to the arms, the star should be orbiting more and more slowly than and why they should orbit more and more slowly, because once we get far enough out from the center, so there is if we concentrate on the stars which are here, so there is no more mass, and the gravitational pull from the center of the galaxy is getting weaker. So we expect to the stars which are farther away from the center of the galaxy has to be moving slowly rather than moving fast. So So you expect to look something like the lower dash line. So if you're moving further from the center of the galaxy, so the speed of the star's velocity should be getting slow. But instead, what has been found is that the rotation speed of the star around the galaxies is increasing and sort of is increasing, and this is sort of flattens out, higher value than would be expected just from the gravity of the stars contained within the galaxy. So this is an evidence that the bulk of the mass in this galaxy was not contained in the stars of these galaxies that we see, but in fact contained in some broader distribution of the dark matter. So like Zwicky, Rubin also found that the galaxies are mostly made up of dark matter, and stars in the galaxies are distributed as sprinkles on the dark matter ice cream cone. So we know now that the dark matter is there because it exerts gravitational pull on the stars, we can see in the galaxies. So now the natural question is that what is dark matter is made of? Is dark matter is made up of atoms? No, it cannot. It cannot be, because if it is, then it should shine and do other kind of interaction. But the dark matter is not doing so. So dark matter must be made up of something other than atoms or quarks, perhaps a new kind of elementary particle that we have never seen before. So the most promising candidate is the WIMP, which is weakly interacting massive particle. It is expected to have mass around 10 to 100 mass of the proton, times of the proton. We do not see them because it doesn't interact with light, but it could interact with normal matter via weak interaction. So scientists are searching for this dark matter particles through deep underground experiments. Now at this stage, we are convinced that yes, there exists dark matter in the universe, and actually the universe is full of the dark matter. So now let us again come to the fact that we know that the universe is expanding, but the natural question comes into mind: does the expansion of the universe is changing over the time? So what do we expect? We know that the gravity is the dominant force on the large scale in the universe. Therefore, uh, uh, it compels us to believe that due to the attractive nature of the gravitational pull between all the matters existing within the universe, uh, we expect that the expansion should be gradually slowed down over the time. But people have tried to measure the slowing down of the expansion, but never could do it because the measurements are very challenging to make. However, in 1998, teams of two astronomers studying the type 1a supernova found the evidence that the expansion is actually not slowing down, it is in fact speeding up. So for that they got the Nobel Prize in 2011. So this is a nearby galaxy in the lower left, looking like something a bright star. This one, that is in fact a star in that galaxy which exploded, and about 3 weeks after it exploded, it becomes nearly as bright as other billions of stars in the galaxy. Supernova is basically an explosion of star. The brightness of the distant supernova show that the universe is expanding. So these are so this is a kind of explosion of a star, which is a supernova explosion, which is an event in which the star exploded, and though they go for being fainter than the sun to brighter than the billion suns over of just a few weeks, and they fade over a course of a few months. So this is these are some supernova, are kind of type 1 supernova, which is basically exploding of the star, which is a kind of white dwarf. I am not going into this detail. So skipping over this the detail, let's come to this plot. The two teams of astronomers have studied type 1a supernova, and, which are all exploded at the same time. You can see these are plotted here, at the same time and having the same luminosity or brightness. So here we have redshifts, here we have the brightness, relative brightness plotted, the scale of the universe, and this time scale, past, present, future. Today we are here. So they study the type 1 supernova, which are all exploded at the same time and having the same luminosity or brightness. So when we know how bright something is, then we can determine how far away it is. So they have plotted how big the universe was when they have exploded. That is the redshift from the spectrum of light, and use the brightness of the supernova to tell that how far they were in the past when they exploded. So at this position, what they expected that this black line that the supernova has exploded when the universe was like about 2/3 its present size will have a particular brightness. These supernovas are going to have a particular brightness, but the point where this shows that instead the supernova went off when the universe had 2/3 its current size. The supernova are about 25% fainter than expected, and that was the indication that the expansion of the universe is not slowing down due to gravity, but in fact the speeding up. So why this is a strange phenomena? Why this is a mystery? Suppose when you throw some objects upward, what happens? It went up and up to a certain height, slowing down and stop due to the gravitational pull of the earth. Then it's come back into your hand. Every time you do this, the same thing happens because gravity is attractive. But what the universe is doing is something different. If you throw a ball straight up in the air, what do you expect? It first slows down, but then instead of falling back to the earth, it starts speeding up and goes out of the atmosphere. That's what the universe appears to be doing, and that is why speed up the expansion of the universe is a mystery. So what could be causing the speed up of the universe? There could be two possibilities. The first one is that the universe is filled with some kind of stuff that gives rise to a repulsive gravity. Gravity is attractive in our solar system, in our galaxy, but perhaps when we're talking about at cosmic scale, there are some additional stuff in the universe which is not dark matter, not atoms. It must be something else which has the property that makes things repel from each other, and we call it now the dark energy. And we think that almost 70% of the universe is filled with the dark energy. So the other possibility is that our understanding of the gravity, which comes from Einstein, is wrong. It acts differently at a small scale, like at our solar system and galaxy. It is attractive in nature, but at cosmic scale, it acts like in a repulsive way. So we now have this picture which is suggested based on the observation and studies within the last 10 to 15 years, in which the 90% of the universe is dark. Means it does not emit any sort of light or interact with light. The stuff we see in our everyday world, stuffs made of atoms and more fundamental particles, quarks, are only 5% of the universe, which are here is the baryonic matter. So you see only 5% of stuff of the universe which we are trying to figure out. 25% is the dark matter that is responsible for holding the galaxies and clusters of galaxies all together, and it is the one with which the structure is getting shape in the universe. The dominant component of the universe is 70%, which is the dark energy, which is gravitationally repulsive stuff and is responsible for the speeding up and expansion of the universe. So what is dark energy? We don't know yet. We think it is a component with negative pressure to make things repulsive. The most conservative hypothesis is that the dark energy is the energy of the empty space, that is the vacuum, which is possible only in quantum mechanics due to Heisenberg uncertainty principle. Classically, we don't have vacuum, don't have any energy. And it turns out that according to the quantum mechanics, the property of the vacuum would have the right property to be dark energy to have the gravitational repulsive effect. But the problem with the hypothesis is that the quantum mechanics predicts that the vacuum energy per unit volume should be infinite. This is not true with the dark energy. This is not feasible. That means some calculations are wrong. So the dark energy is still a fundamental mystery. There are other suggestions that the dark energy could be a different kind of field like Higgs boson, but much lighter than the Higgs boson. But all these ideas are only the speculations. So we do not know that what is the dark energy still. Since it almost 70% of the universe is filled with the dark energy, now will be more dominant in the future as expected. So the nature of the dark energy will determine the future evolution of the universe. So that's why the dark energy is very important. Now we know that about the dark matter and dark energy and their roles for holding the galaxies and clusters of galaxies of the universe and accelerating the expansion of the universe. So okay, let us come back to the point that the universe is expanding. That means the universe was smaller yesterday and it was even smaller the day before that. Therefore, at some point of time, the universe had to have been infinitely small. So let us trace the expansion backward in time. What would we expect? The universe had a beginning. This beginning is what cosmologists called the Big Bang. The Big Bang model as the origin of the universe is the most widely accepted model amongst the multiple scientific models presently available because it has explained and predicted the most observation about the universe. George Lemaitre, who was the Belgian cosmologist and Catholic, was the first to give the idea about the Big Bang. And the universe at the time of the Big Bang was like this. You see, it's infinitely hot and dense singularity, which was only a few millimeters wide, similar to a supercharged black hole. But about 13.7 billion years ago, this tiny singularity exploded violently. And what we see something like this in the present universe, in fact the observable universe. So from this explosion we came up with four major components: matter, energy, space, and time. So there are two major stages. So in the evolution of the universe after the Big Bang, known as the radiation era and the matter era. The shape of the universe we see today is outcome of the key events of the two main era of the universe existence. Let us start with the first era, which is the radiation era. In this era, which is just after the Big Bang, is dominated by the radiation and energy. No existence of matter was there. This era is made up of small stages, which is called epochs, that occurred within the universe's first tens of thousands of years. These epochs are Planck's grand unified, inflationary, electroweak, quark, hadrons, leptons, and nuclear. So the earliest, this is the timeline of the Big Bang, and this is Big Bang. and these are the radiation era, components of the radiation era. The earliest is the Planck epoch. You can see here the temperature at that time is 10 to the power 40 Kelvin, and that is immediately after the Big Bang. Do you know the Planck era only occurred briefly after the Big Bang? But how briefly? Actually, it was less than 1/4 of a second. So how brief is that? In fact, it is 1 followed by 45 zeros. In other words, too brief for us to understand. In this era, no matter existed, which is only energy, and the ancestor of the four forces, gravity, strong nuclear, weak nuclear, and the electromagnetic, which are known as the super forces, existed. At the end of this stage, however, a key event occurred, and the gravity force split away from the super force. And next come the grand unification epoch. You can see the temperature and the time of this period, and this is named after the three remaining unified forces: strong, weak, and electromagnetic. So the unification of the strong, nuclear, weak, and electromagnetic force that existed during this period of time is referred to as electronuclear force. This epoch ended when one of these forces, called the strong nuclear force, broke away, and the unification of the weak nuclear and the electromagnetic force that existed at this time is referred as electroweak force. So then come the inflationary epoch, which began, in which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of an orange. The universe at this time was very hot, and it was filled with electrons, quarks, and many other particles which were free. Inflation epoch actually smoothed out the universe. Inflation has caused a massive increase in scale, diluting the space-time curvature, which in turn has solved the flatness problem. We will discuss this later. Then came the electroweak epoch, and the electroweak era happens after the three full epochs after the Big Bang. The universe was still a dark, young, and chaotic place. Fortunately, the universe finally started becoming quasi-recognizable during this epoch, but this comes dramatic changes too. In fact, the whole thing inflates, and even basic particles are born. Finally, the last two forces, weak nuclear and electromagnetic, finally split off, and the four individual forces of the universe break free during the electroweak era. And during the next stage, the quark epoch, all the universe ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then in hadron epoch, the universe cooled down enough to bind the quarks together to form protons and neutrons. Then comes the lepton and the nuclear epoch. These are the radiation era last two stages in which the protons and neutrons underwent significant change. They fused and created nuclei, and in doing so, they created the first element of the universe, which is the helium nuclei. The lepton epoch was the period in the evolution of the early universe in which the leptons dominated the mass of the universe, and it started roughly 1 second after the Big Bang, after the majority of hadrons and antihadrons annihilated each other at the end of the hadron epoch. But in nuclear epoch, first few minutes, protons and neutrons fuses into nuclei, and by the time the universe is about 15 minutes old, much of the helium had been transformed. So The universe's new ability to form elements, the building blocks of matter, created a matter era. Much as the name suggests, the matter era is just the presence and predominant of matter in the universe. It features three epochs that took almost billions of years, the vast majority of the universe lifespan, including the present universe. The three epochs are atomic, galactic, and stellar. So our first was is the atomic epoch. That time the temperature was 300 Kelvin, and it was the first atomic epoch. At this stage, the temperature of the universe cooled down enough for electrons to get these are the electrons, and these are the protons. So electrons, so temperature of the universe was cooled down enough for electrons to attach the nuclei for the first time, which is called the recombination process. And this process helps create the universe elements hydrogen. This is the proton, and the electron is revolving around this. So during recombination process in the atomic epoch, we have the existence of the hydrogen atom. This hydrogen, along with the helium, which were earlier existing existed there, dotted the universe with atomic clouds, and that is the galactic epoch. Within the clouds, small pockets of gas may have had enough gravity to cause the atom to collapse, and these cluster of atoms formed during the galactic epoch become seeding of the galaxies. So these helium and hydrogen form gives rise to the formation of the galaxy. Nested inside these galaxies, stars begins to form, and in doing so, they cure the latest and the current stage of the universe development, which is known as the stellar epoch. Okay, the formation of stars then caused the tremendous ripple effects and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turns, these elements become the building block of the planets, moon, life, everything we see today. And this ecosystem of everything was only possible because of the stages in the development of the universe. So you see here, after the Big Bang, we have inflation and different stages, and now we are here, and the Hubble Space Telescope and the WMAP, the Wilkinson Microwave and an Astroperiod probe are taking the picture of the present universe.